Welcome to lecture 17 on graph theory. In this lecture, we will learn max flow mean cut theorem. This theorem essentially proves that Ford-Fulkerson algorithm is correct. Please recall that in the previous lecture, we learned what is a cart, what is the capacity of a cart, what is flow across a cart, and we proved a lemma which says that for any given flow in a network and any given cart, the flow value is less than, the flow value is equal to the flow across the cart. Okay. So, we proved the lemma, which is we denoted lemma 1, which essentially says that the value of a flow is equal to the flow across the cart S complement. Okay. So, next we prove another lemma, lemma 2, let F be any flow and let S complement be any ST cart. Then the value of the flow is less than or equal to the capacity of the cart S complement. Okay. We will prove this lemma now. So, what we know is that the value of a flow is equal to f of E out of S minus f of E for all E into S, right. Now, here this is always a positive quantity, it is a flow is positive because the capacity is positive. So, I can write that the flow value is less than or equal to f of E out of S. That means, I am just ignoring this term, this positive term, right. And also we know that this is the capacity rule, that the flow is always less than or equal to the capacity, right. So, from here this is the capacity rule that we learned. This is the first rule for F to be a flow. Then what we can do is that this term is smaller than or equal to, I replace all F by C now, capacity. So, this is E out of S. And if you recall the definition of capacity of a cart, this is the definition. So, that is why this is equal to the capacity of the cart S complement, right. Now, we just state another lemma. Let F be any flow in G and S complement be any ST cart. Now, what we know is that always see this is true that the flow value is less than or equal to the capacity of the cart. Now, if flow value is equal to the capacity of some cart of the cart S complement, then F is max flow and S complement is minimum cart, right. This is sort of consequence of this lemma, because for any arbitrary flow and arbitrary cart this is true, but when this equality holds here, that is the maximum flow and the corresponding cart is the minimum cart. Also, if you remember the previous example, I am not drawing it again, where we took S is equal to S A C. Please refer my example in the previous lecture, and S complement was B, D, E and T, and the capacity of this cart S complement was 3 and flow across the cart S complement was 2, which is also the flow value. So, you can see that this is true, that the flow value is less than or equal to the capacity of the cart S complement. Okay, so with this with these 3 lemmas, now we are sort of ready to prove the max flow mean cut theorem. So, now I will state max flow mean cut theorem and prove it. So, this is max flow mean cut theorem. If F is a flow in a flow network G with source S and sink T, then the following are equivalent. Okay, the first statement is F is a max flow in G. The second statement, the residual network with respect to the flow F, that is G F, contains no augmenting path. And the condition C is the flow value equal to the capacity of cut S complement for some cut S complement. Okay. So, the flow is a maximum flow in G if and only. So, this theorem says that the flow is maximum flow in G if and only if there is no augmenting path in the residual network G F. Okay. So, this is a sort of the correctness proof of the algorithm, Ford-Fulkerson algorithm, because there, if you remember, the stopping criteria was when there is no augmenting path in the residual network, then you stop because you can't improve the flow anymore. So, A implies B, B implies A. This is this sort of proves the correctness of Ford-Fulkerson algorithm. So, that we will do first. We will prove that A implies B and B implies A. Okay, so, the proof is in this way. So, A will prove that A implies B, B implies C, and then C implies A. So, that means all these conditions are equivalent. First, we will start with A implies B. Suppose that means F is a maximum flow in G, then we will prove that there is no augmenting path in the residual network G F. Suppose for the sake of contradiction, that F is max flow in G, but G F has an augmenting path. P. If this is true, then there is an augmenting path P in the residual network GF, then we can augment delta p amount of flow. This is the capacity of the path p greater than 0. We can augment delta p unit flow along p and get a better flow. Which contradict F is max flow. Okay, so, what we have proved is that F is a maximum flow, then we have proved that there can't be augmenting path in the residual network GF. This is A implies B. Now, we will prove B implies C. Let us move to the next page. B implies C. So, B says that the residual network does not have any augmenting path. So, suppose GF has no augmenting path. Okay. Well, so what I want to do is that I want to draw the figure again. This will be helpful to explain this proof of this is the source node, this is node A, B, C, T, D and E, and I know the maximum flow of. So, I directly write the max flow. This is the flow I am talking about, the flow F along CT. Flow is 2, capacity is 2. Along SP, flow is 1, capacity is 1. From B to C, flow is 0, capacity is 5. B to D, flow is 1 and the capacity is 4. D to E, flow is 1, capacity is 2. E to T, flow is 1 and the capacity is 3. Right. Now, I know that this flow is maximum flow, because this is the flow that we obtained from Ford-Fulkerson algorithm. Now, let me also draw the residual network for this one. So, S A, B, C, T, D and E, these are the vertices of the residual network. The forward edge of capacity 1, so backward edge of capacity. Okay. I draw use red color for the backward edge. So, the backward edge is capacity 2, forward edge capacity 1 and backward edge capacity 2, only a backward edge of capacity 2, and here also only a backward edge of capacity 1, and then B to C you have a forward edge of capacity 5, B to D you have a forward edge of capacity 3 and a backward edge of capacity 1, forward edge capacity 1, backward edge capacity 1, forward edge capacity 2, backward edge capacity 1. Okay, so this is my GF residual network, and this is the network and the flow. Okay. So, B says that suppose GF has no augmenting path, of course, this GF has no augmenting path, you can't find a path from S to T here. Okay. Then you define a set S. So, our aim is to find a cart S complement such that for that we will prove that the flow value is equal to the capacity of that cart S complement. This is what the C is. So, we are defining that, we are sort of constructing that cart here. So, S is the set of vertices in the network G such that there exists a path from S to V, those edges only. Now, let me explain what is the definition of S here. So, S is in this example, S is the set of vertices which are accessible from S. That means, there is a path from S to A, those vertices only. So, the S consists of the source node itself, because you can sort of S to S, and then from S you can go to A using this forward edge in the residual network. Sorry, I forgot, path from S to V in GF, this is important, in the residual network. So, S consists of S source network and A, because A is, there is a path from S to A, and also there is a path from S to C. So, C will be in the set S. Now, we can see that there is no path, you can't reach to B from S, starting from S you can't reach to B, there is no path to B. So, B, D, E, T, those vertices will not be in the set S. So, I hope that you understood what is this S is, and obviously, S complement is equal to B minus S. So, we have defined how to construct this cart, and then what we have to prove is that we have to prove that the capacity of this cart is equal to the flow value, in order to prove that B equal to C. Now, few things, this S complement is a ST cart as S is in S and T is in S complement, which is clear. So, here your S complement is B, D, E, T. So, the cart we have defined in general, this is a ST cart. Our final goal is to prove that the capacity of this cart that we have defined is the flow value. Okay. So, we will make some observations. First, for each edge u v in S complement, that means u is in S and v is in S complement. So, let me okay, for each edge what is true is that we have flow along this edge u v is equal to the capacity of this edge u v. This is what we are claiming. Now, let us see whether this is true for this example. Let me take one edge of this form where u is in S and v is in S complement. So, one such edge is okay, the cart that we got is that this one, right. So, this is your S, this is S and this part is S complement. So, consider an edge say CT is an edge from S to S complement, and then you can see that for this cart, for this edge the flow value is equal to the capacity, and the another edge is of this form is SB. SB is also from S bar. So, S is in S and B is in S bar. For SB also the flow value is equal to. Why this should be true in general? Because if the flow is strictly less than the capacity, then there will be a forward edge from U to V or C to T. Then T will not be in S, then T will be in S itself, right. So, this is true, otherwise as I said, otherwise there will be a forward edge u v in the edge of the residual network. If this is not true, if they are not equal, there will be a forward edge from S to B, then B will be according to the definition of S, B will be in S, right. So, otherwise there will be a forward edge which would place V in S. I hope that this is clear, and we will make another comment about the edge of the form which is from S bar to S. Now, for each edge V u which is from S bar to S. So, one such edge is S bar to S is BC. BC is an edge from S bar to S. So, BC is an edge from S bar to S. So, for each such edge we must have the flow V u must be equal to 0. And you can see that the flow B C, the flow along B C from B to C is equal to 0. Now, let me explain in this example why this should be always 0, because if this is not 0, suppose this is 1, then there will be a backward edge in the residual network from C to B. Suppose instead of 0, it is say 1 and the capacity is 5. Then this will be 4, the forward edge capacity will be 4 and there will be a backward edge of capacity 1. That means, the B will be in S then, right. So, B will not be in S complement. So, I hope that I tried my best to explain this one using the example. So, this should be true for any edge from S bar to S. Otherwise, we would have a backward edge u v in the residual network with capacity C f u v equal to f of v u. Right, which would place V in S. So, here my V is B and U is C. As you can see from here, if instead of 0, if it is 1, there will be a backward edge with capacity 1, and that will, this backward edge will make B, or in general V, to be in S, because B will be accessible from S then, right. So, that is why for each edge which are from S complement to S, this must be true, and for each edge which is from S to S complement, this would be true. Now, let me just remove all this, right. So, I hope that you understood these 2 points, right. Now, we will prove the therefore, we wanted to prove that this flow value is equal to the capacity of S complement. So, let me start with the definition of the flow value, the value of the flow, which is, as we know, that in terms of the cut, it is the flow across the cut. This is by lemma 1. So, F E out of S minus F of E into S, right. This is by using lemma 1, because the lemma 1 says that the flow value is equal to the flow across the cut S complement, and this is the definition of flow across the cut. Now, this E into S means these are the all the edges of the form, they are the edges of the form S to sorry S bar to S, and we have just proved that if an edge is from S bar to S, then the flow value is equal to 0. So, F E is 0 for all such edges, right. So, this is equal to F of E out of S. Right. So, just now we proved that if V u is from S bar to S, that means it is an edge into S, then f of V u or f of E is equal to 0. This is just we proved in the previous page. Now, the other one is that the E out of S, that means for all edge u v of the form from S to S complement, that is the edge out of S, the edge is going from S to S complement. For such edge, what we have proved just now is that the flow value, the flow of u v is equal to the capacity of u v, right. Then what I can do is that I can replace this flow by the capacity. So, this is equal to C E. I am sure that you understood this one, E out of S, and this is the definition of the capacity of the cart S complement. If you look at the definition of the capacity of the cart. So, this is C S complement. Okay. So, in this part what in order to prove that B implies C, B is the condition that the residual network does not have any augmenting path, and then we described here a technique to find a cart for which the flow value will be equal to the capacity of that cart. Okay. So, if there is no augmenting path in a residual network, then you can always find a cart for which the capacity of the cart is equal to the flow value. That is what the B implies C we proved just now. The last part that is left is that we have to prove that C implies A. Okay. So, the last one is C implies A, or B is also fine. C implies say B, no, C implies A, that is what we have to prove. Okay. C implies A. Now, by lemma 2, what we know is that the flow value is always less than or equal to C, the capacity of an arbitrary cart for all carts S complement. Thus, the condition C says that there exists a cart for which f is equal to this, the flow value is equal to the capacity of the cart. The condition that there exists a cart for which the flow value is equal to C capacity of that cart. Thus implies F is maximum, because F is always less than or equal to the capacity of the cart, and when the equality hold, that is the maximum flow. Okay. So, we have proved the maximum flow mean cut theorem. So, given a network, we know how to find maximum flow in the network using Ford-Fulkerson algorithm, and also given a network, we can find the minimum cut using the concept of residual network and augmenting path technique. Now, I give just one more example. If you remember that we started with one network and then I just wrote a arbitrary flow in that network. Let me see whether the flow value that arbitrarily we have assigned, that is the maximum flow or not. Refer my first lecture on network flow. So, the example is this one. We considered this network, and at that point of time I did not say I said that this is just a flow and the flow value is 2. We could not comment on whether that flow is the maximum flow or not. Let us see, this is the example taken from the first lecture on network flow. The flow I assigned was 1 3 1 1, flow 1 capacity 3, and here it is 1 flow value capacity 3, 1 flow value capacity 1, 1 3. From A to C, flow is 0, capacity is 2. From D to A, the flow is 0 and the capacity is 2. From D to B, flow is 0 and the capacity is 2. Now, this is the example I took at the very beginning. Now, we know that the value of the flow is equal to 2, but it is not clear whether this flow is the maximum flow or not. So, to check that, what we can do is that we can just, so this is an arbitrary flow, say for example, and we can compute the residual network with respect to this flow, right. So, let us draw the residual network of this network with respect to the given flow. Well, so there will be a forward edge capacity 2, and let me draw the backward edge also using the same color. Yep, it does not matter. So, the backward edge has capacity 1. A to B, there is no forward edge, there is a backward edge of capacity 1. B to T, there is a forward edge of capacity 2 and a backward edge of capacity 1. S to C, there is a forward edge of capacity 2 and a backward edge of capacity 1. C to D there is no forward edge, there is a backward edge. D to T there is a forward edge 2 and there is a backward edge of capacity 1. A to C there is a forward edge capacity 2. D to A there is a forward edge of capacity 2 and D to B there is a forward edge of capacity 2. So, this is the residual network of the network G with respect to the flow. Now, can you find augmenting path here? Can you find a path from S to T? Okay. So, start from S, you can go to A, from A you can go to C, and from C you can go back to S only, right. So, start from S, you can go to A using this edge, forward edge, and then from A you can at most go to C using this forward edge, and from C you can go to S again using this backward edge. This is true even if you start from S to C first and then again go back to S. So, there is no path, so no augmenting path. Sorry, no augmenting path. In GF. So, then by Ford-Fulkerson algorithm we can say that the flow value, the flow that we have started with, which is having the value 2 is the maximum flow. You can't improve the flow value because there is no augmenting path in the residual network. So, the max flow here, this is the max flow. So, this is the max flow, and now here can you find the minimum cut? Yes. So, by the proof of max flow main cut theorem, the way we find the minimum cut is that you define a set S. S is the set of all vertices which are accessible from the source node. So, the source node is S, and the vertices which are accessible from S are A and C. So, the S consists of these 3 vertices S, A and C, and definitely then obviously that S complement is B, D and T, right. And so, the cut is here. So, this is the cut. So, this is the cut, right. This is S, this is S complement. Now, what is the capacity of this cut? The capacity of this cut S complement is the edges which are going out of S, the capacity of A B plus the capacity of C D, right. These are the only 2 edges which are going out of S, C D, and the capacity of AC is equal to 1 and the capacity of CD is also equal to 1. So, the capacity is equal to 2, and you can see that since this is the minimum cut, the capacity of this minimum cut is S complement is equal to the flow value, which is equal to 2. Okay. So, from this lecture on network flow, what we know? We know that given a network, how to find the maximum flow in the network, and also given a network, we also can find the minimum cut in the network, right. And we know that the maximum flow value is equal to the minimum cut value. This is what the maximum flow mean cut theorem is. Thank you very much.